Hi guys, good morning. Hope you're all doing well. Three of you are there. I'll casually wait for 2 more minutes. Let your friends join.
हाँ वो जल्दी बोलो.
Okay, so I don't think your friends are joining, so we'll start right away. Right? Let me share my screen. So yeah, we are almost at the verge of completing equilibrium, as I told you. So we saw so many things last class, right? So we saw what are the properties of equilibrium constant, what are the different types of equilibrium constant, Kp and Kc, right? And what is the relationship between them, right? And we also saw how to approach the problems, right? And then now we're going to deal with some small part, and then we'll do some problems, and then this part of the chapter is over. Then we'll go for ionic equilibrium, right? Okay. So now you're going to see a case, or now you're going to see the story where how is it that, or is it possible for me to disturb the equilibrium? And assume that there's a reaction, right? So that reaction has reached equilibrium, right? So what and all are the ways in which you will be able to disturb the equilibrium, in the sense that again the reaction is going to happen. Disturb the equilibrium means the reaction is going to happen again after some point of time. Again, it will reach equilibrium eventually. That is for sure, right? So two things you have to understand, right? One thing is what are the ways in which I'll be able to disturb equilibrium? Okay. Second thing is that if I disturb the equilibrium, which side the reaction is going to move, either forward direction or backward direction. Hope you understand the two stuff. That's what you're going to see. Again, I repeat. One, what are all the ways by which you'll be able to disturb the equilibrium? Second, if you disturb the equilibrium, which side the reaction is going to move, either forward or backward? Again, eventually it will reach equilibrium. That is for sure. Right? Fine. So for me to help with all this, right, I would say the second part, dealing with the second part, that is, if I disturb the equilibrium, right, which side the reaction is going to move, is given by a scientist called as Le Chatelius. Right? And obviously, this is the principle given by him. So it's called Le Chatelius principle. Okay. So please take down the statement, people, for Le Chatelius principle. I'm going to give you a statement. Please take down the statement. Right. So if there is an effect which causes or right, which disturbs the equilibrium, if there is an effect which disturbs an equilibrium. The reaction will move, the reaction will move in a direction. The reaction will move in a direction such that the effect is minimized or opposed, such that the effect is minimized or opposed. Okay, so if you just go to the statement one, we'll just read the statement, guys, right? So it says if there is an effect, right? If there is an effect which disturbs the equilibrium, yes, right? So we'll see what are all the effects later, but if there is an effect which causes a change in equilibrium, right? So how the reaction is gonna move, right? Which direction is gonna move is given by this. How the direction is going to be in such a way that the effect which is causing the change in equilibrium should be minimized or opposed. For example, if you did something, for example, you increase the temperature, for example, right? You increase the after the reaction has reached equilibrium, right? You have increased the temperature, right? Now the reaction is going to move in such a direction where it will do something that the temperature is going to get decreased. That's what I'm saying. It is going to move in a direction where the temperature will get decreased. That's what I'm trying. Or say you have, after the reaction has reached equilibrium, right? You have added more amount of reactants. So what is the effect now? The effect is increase in concentration of reactants, right? So obviously what the reaction will do, the reaction is going to move in such a direction that this effect, what is the effect here? The effect here is increase in concentration of reactants. That effect is minimized, right? So obviously now what's your guess? If I want to oppose or minimize this effect is what? Effect is increase in concentration of reactants. Which side I should move? Any guesses? Forward or backward?
Forward.
Definitely, right? So what is the effect here? Effect here is increase in concentration. So the equilibrium will change the direction where I can decrease the concentration of the reactants, and obviously that will happen in the forward direction, right? So that's what Lee-Chartelis principle says. Okay, you can either use Lee-Chartelis principle or you can use logics, right, which I'm going to give you in all the cases, right? Either way, you're going to get the same answer, right? So now we'll see what are all the ways by which you'll be able to disturb the equilibrium. Okay, right? Fine. So first one under this is addition or removal minus, right? Now addition or removal of reactants or products. So there are so many things involved here. Addition of reactants, addition of products, removal of reactants, removal of products. So all I can see under one thing, right? There are four cases here, right? So all of you don't have to worry much. Like this is going to be very easy, right? Say there is a reaction like R giving P, that is reactants giving products is a reaction, and this reaction has reached equilibrium, and obviously it's a reversible reaction, right? Okay, say now I'll take an example where after, now we already saw the example of increase in concentration of reactants. What will happen? It is going to move in the forward direction. Now let me see it in another way. Let me see it in a mathematical way. We'll see what happens. Okay, so what I'm going to do now, this will have an equilibrium constant, isn't it? Kc, right? This will have an equilibrium constant, right? And this is going to be a constant. This is going to be a value which is irrespective of what was the initial concentrations of reactants and products. We all know that was one of the properties of equilibrium constant, isn't it? Right. So now this is in equilibrium. Now you're going to disturb the equilibrium by increasing the concentration of reactants, right? So now the reaction is not at equilibrium, but the equilibrium constant value is going to be similar, no doubt about it, right? But since I am not going to be calling at this is not at equilibrium, I cannot use Kc, I have to use Qc, isn't it? Right. So now this Qc, now say initially when the equilibrium was there, right? Say it was something like this, right? So when the equilibrium was there, I'll be able to represent it like, say, P, that is the product concentration, divided by R naught. Say R naught was the concentration of the reactants at equilibrium. Okay, R naught is the concentration of reactants at equilibrium, right? So now what will happen? Basically, you have increased this part. Okay, so now again the product concentration is same, but the reactant concentration has decreased, say R1, right? So obviously I know R0 is lesser than R1, right? So when I compare QC and KC, which is higher, which is lesser? Tell me. Hmm? So what I'm trying to do, basically I am increasing the denominator. That's what I'm doing here. That's how you get this value, right? So if I increase the denominator, obviously this value would have gotten decreased to QC. So what you see here is QC is less than KC. And we know what is going to happen if QC is less than KC. What will happen? Forward reaction will happen. Just now, the last class we saw, when QC is less than KC, forward reaction will happen. Right? So either you use the Chart-less principle, or you use your QC, KC, all these things. You're going to end up with the same answer. Right? Same way, if I'm going to do, for example, say increase the concentration of products, keeping the reactant concentration same, right? Say now what will happen? Something like this will be there. Say I call this as P naught when it is at equilibrium, the product concentration, right? Now I have increased the concentration to say P1, right? So obviously I know that this value is increased, the numerator is increased. That means the QC value in this case will be greater than KC, right? So now greater than KC, I know what will happen. It is going to move in backward direction, right? Or you can use the Lee-Chatelain principle. What are you doing? The effect you're doing here is increase in concentration of products, right? So the reaction will move to suppress it. Suppress it in the sense I'm going to decrease the concentration of products. What is the only way? Only way is if this moves in the backward direction, I will be able to decrease the concentration of products. Yes, I hope everybody understood the first one. The first one is increasing or decreasing the concentration of reactants or products. And either you can use QC or Lee-Chatelain principle to get which side the reaction is going to move. Right. Okay. Moving on. Next one. Any questions, guys? You want to ask me? I hope everybody understood. If you have any doubts, please stop me right there and ask. Okay. Right. Next one. Uh, okay. So next what I can take. Okay. Change in volume I'll take. Okay, so what do you mean by change in volume is, say you have a reaction and the reaction has reached equilibrium and you're going to change the vessel. Obviously, the volume we are talking about is volume of the vessel, right? So after the reaction has reached equilibrium, say you transfer the contents from a 3-liter vessel to a 5-liter vessel, right? So obviously you will definitely see that there will be some change in equilibrium, but not for all reactions. Now this I'll be able to see in 2 ways, right? Say I have delta N is equal to 0 kind of reactions, right? And delta N not equal to 0 kind of reactions, right? Two types I can see, right? Now I think I already mentioned about this, right? Delta N equal to 0 kind of reactions. You know that all the volume terms will get cancelled. Hope you remember, we saw last class, right? So like if I can show you, guys, do you remember? I want me to show you. Do you remember that when I have delta N is equal to 0, all the volume terms in the Kc equation gets cancelled? Yes or no?
Yes.
Right. Hope everybody remembers, right? If anybody doesn't remember, please tell me. I'll show you. I have the pages with me. Right? You want me to show it? We'll try. Okay, let me check. Where is it? See here, right? So you took delta N is equal to the H2 plus I2 giving to HI reaction. Now you see if I write the Kc equation, how is it? And then this is molarity. Now I convert it into number of moles and volume, right? So you see that all the volume terms are getting cancelled, right? So what do you mean by that is, right? What do you mean by that is, if I have delta N is equal to 0 kind of reaction, change in volume has no effect, right? When I have delta N, because in Kc equation, there is no volume term, isn't it? Right? So when you have delta N is equal to 0 kind of reactions, please be very careful in these kind of questions. First check for delta N, right? If it is not, if it is equal to 0, change in volume or change in pressure for that matter, right? You will not see any effect on the equilibrium, right? But delta n not equal to 0, definitely you will see that you will have some effect, right? So again, this can be two cases, isn't it? I can have either delta n greater than 0, right? Or I can have delta n to be less than 0, right? So we'll take both one example for this one example, for this one example, and we'll see what is happening. Okay, right. So let me take some examples. Say delta n greater than 0, that means product should be more. Say I can take this. So I can take PCl5 giving PCl3 plus Cl2. Is it not? So you see there is 1 plus 1, 2. Here I have only 1. 2 minus 1 is 1. So delta n is greater than 0. Okay, right. So let me write the Kc equation directly, right? So Kc equation, I know concentration of this divided by concentration of this. I directly write in terms of number of moles and volume, right? So it will be number of moles of PCl3 divided by volume into number of moles of Cl2 divided by volume, right? Divided by what is there? PCl5, number of moles of PCl5. Okay, PCl5 divided by the volume. Okay, right? So bear with this, guys. Some problem is there in this area. Okay, anyway, so this is PCl5, right? So what do you see? There is one volume term getting cancelled. There is one more volume term left, right? Now what I do is say I'm going to increase this volume, right? I'm going to change the vessel, right? I'm going to put it to a 3-liter vessel to a 5-liter vessel, right? So I'm going to increase the volume, right? So what will happen if I increase the volume? Can I say this term is increasing? So can I say this term will decrease, right? And if this term that is in the numerator, the overall numerator is decreasing, so what will happen to Kc? Kc will also decrease, and it is, I mean, Kc will decrease means it is not anymore Kc. It is actually going to be Qc, right? So what happened? Now comparing Qc and Kc, you have decreased the value of Kc to Qc. So obviously Qc value will be lesser than Kc. Right? So now what will happen? Obviously it is going to move in the forward direction. Okay, it is going to move in the forward direction. Hope everybody understood what I did here. I wrote everything in terms of number of moles by volume. I cancelled whatever volume terms I can cancel. Then I'm going to increase the volume. If I increase the volume, so you see this way, this term will, volume will increase. This entire term will decrease. Numerator, so overall numerator is decreasing. So Kc will not be Kc anymore. It will decrease to Qc. And obviously when I compare these values, it will be Qc lesser than Kc. So obviously forward direction. Right? Now, if you find any reaction where delta n is less than 0, right? So what will you see there is in the denominator, right? In the denominator, there'll be one volume term, and that if you increase, right? That if you increase, you will find that this overall term is decreasing, and then you will see that the Kc value will be increasing to Qc, and you will eventually see that it is going to be backward direction. That is for delta n less than 0, right? And if you ask me, sir, do I have to remember all this? Is there any way that is there any shortcut which I can remember? Absolutely. We have one shortcut and I'm going to give you that. Please take down, guys, the shortcut, right? Please take down the shortcut. Increase in volume. This is only for increase in volume, okay? Decrease in volume will be exactly opposite. Whatever I'm going to tell, for increase in volume, decrease in volume will have the exact opposite effect. Okay, fine. So increase in volume will shift the reaction increase in volume will shift the reaction to the side, to the side which has to the side which has more stoichiometric coefficients, which has more stoichiometric coefficients. Right? I think it makes sense, isn't it? So if you increase the volume for a delta n not equal to zero kind of reaction, the reaction is going to move to the side where I have more stoichiometric coefficients. Now you can see for this particular reaction, if when you increase the volume, I said that it is going to move in the forward direction, right? How you see the total stoichiometric coefficient on this side is 2, this side it is 1, right? If delta n is equal to 0, this side, reactant side, I would have had more, what is that? More stoichiometric coefficients. So that side, the reaction would have gone, that is backward, right? So this is the shortcut. If you increase the volume, the reaction will move to the side which has more stoichiometric coefficients. That's what you need to remember. Okay, right? Now the next one, I mean, you saw two things now. One is first one is addition or removal of addition of products and reactants, and next one is change in volume. Is there any questions, people? Hope everybody understood this also, right? Only the you can just remember the shortcut and obviously the logic behind it also, right? Okay. So the third one, which is going to disturb my equilibrium, is change in pressure. Right now, again, you have delta n equal to 0, delta n not equal to 0, right? So again, delta n equal to 0 kind of reactions are not going to have any effect. Okay, right? Now, why is it like this? Because I know pressure is inversely related to volume, isn't it? The pressure is inversely related to the volume. Okay, right? So obviously, delta n equal to 0 kind of reactions will have no effect in change in pressure as well as when you change the volume, right? But delta n not equal to 0 definitely is going to have the effect. And whatever you saw for volume change, right, the exact opposite you will see for pressure change, right? So again, I'm going to directly give you the shortcut, people. Please go for it. Increase in pressure. Take down the statement. Increase in pressure. Increase in pressure will shift the reaction to the side, will shift the reaction to the side which has lesser stoichiometric coefficient. Just exactly opposite of what you saw in volume, right? It is going to shift to the side where which has lesser stoichiometric coefficients. Okay, so if I ask you, if I have this reaction N2 plus 3H2 giving 2 ammonia, and I say that I increase in pressure, which side the reaction will move? Tell me. Forward or backward? Yes, forward, right? Because you see there is 2 here and there is 1 plus 3, 4 here. So definitely lesser stoichiometric coefficient is 2. So it will move in the forward direction. Okay, easy, right? Now, change in volume is okay. Change in pressure is okay. The next one. The next one, what is the temperature? Definitely, right? Increase or decrease in temperature. Right? Okay. Now here, I have to see it in two different ways, but not in terms of delta n, whether the reaction is exothermic or whether it's endothermic. Depending on that, you will have different effect. Say, for example, increase in temperature. If you do for an exothermic reaction, it is going to move in backward direction. Anyways, we'll see how it goes. Right. Okay. Say, now I'll take an exothermic reaction first. Right. Okay. So now how can I represent exothermic reactions? Say reactants will give me products, and along with that, there is going to be some amount of heat. Right. And along with the product, there is some amount of heat avoided. That is what is called as an exothermic reaction, isn't it? Say now, if I increase the temperature for an exothermic reaction, what is happening? Can I say the amount of heat? see, reactants, products, everything is in the same vessel. Don't think like reactants is on some other vessel, products in some other vessel. No, these are in equilibrium, right? They will be in the same vessel, right? So what I was telling, so we are going to increase the temperature, right? So when I increase the temperature, can I say that the heat which is coming out is also going to get increased, right? So now what you have to consider is consider heat as one of the products itself, right? So that will make it easier for you, isn't it? So when I consider heat as one of the products, and when I'm going to increase the temperature, the heat is also going to increase, or I can say that the product is increasing. And if product increases, I know which side the reaction will move. It is going to move in the backward direction, right? Or you can use Lee Chartier's principle, or you can use common logic itself. Whatever in exothermic reaction, right? It is already heat evolving, and if you supply heat to the reaction, right? So obviously it is going to move in the backward direction. It makes sense, isn't it? Or you can see it in this way: reactants giving products plus heat. So when you increase temperature, heat increases, and considering heat as one of the products, right? So product concentration is increasing, or I cannot call concentration, say the amount of products are increasing, right? So I would say that it is obviously going to move in the backward direction, right? So same analogy will work for endothermic, isn't it? How will they represent it here? R plus heat. What happened? R plus heat. Oh God. Why? Sometimes it happens. I don't know. Okay, so R plus heat is gonna give me my products, right? So this time, if you increase temperature, right, you are gonna increase the heat again, right? So this side heat is in the reactant side. You're increasing the concentration. You're increase the amount of reactants. So this will definitely move in the forward direction, isn't it? Right? This will definitely move in the forward direction. Done, right? Or you can say logically, endothermic reactions require heat, and you are supplying more amount of heat. So definitely it is going to move more and more in the forward direction. Okay, right? So done. That's about temperature. Now there's one more. Actually, there are two more. Next one, sixth one. Sixth or fourth? Fifth one. Right. Okay. Right. This one is addition of an inert gas. Right. After the reaction has reached equilibrium, I'm going to introduce an inert gas into the system. And obviously, along with products and the reactants, there is going to be one more inert gas, like say argon, neon, something, helium, something like that. Okay. You can see, obviously, they are not going to react, right? They will not react with the reactants and products, but they will have some other effect. We'll see how are you going to visualize this, right? So now I'll be able to visualize this in two ways, or two conditions, I would say, right? One, under constant pressure conditions. That means the total, say, assume that this is a closed vessel. Oh, okay, we'll come back to that later. Fine. Under constant pressure conditions and under constant volume conditions. Okay, under constant volume or under constant pressure, I'm going to introduce an inert gas after the reaction has reached equilibrium. We'll see what is going to happen. Okay, right. So let me take first constant volume and then we'll go for constant pressure. Right. So now, or I would say it's better to do the constant. Okay, fine, no issues. So constant volume I have. Okay, so what do you mean by constant volume? That if there is a container, right, and this container is actually sealed here, it's sealed here. That means there it cannot, this cannot increase or decrease its size. That's what it means, right? Constant volume, the whatever the volume is there is going to be constant, the total volume, right? Say assume that you already had N2. Actually, 1 second, guys. Let me bring a bigger box that I'll have some space. Right. Okay. So you already had N2, for example, N2H2 and NH3 already in equilibrium. Okay. The reaction has been completed. Right. So now what you do, this is a constant volume. The volume cannot change. Right. So this will already have some pressure, isn't it? All these three put together. right? All these three put together, say now I would have had this thing, some pressure, P total. Correct? Now you are going to introduce, say, helium gas to this, right? So what is going to happen if you do that? Right? If you do that, what will happen? So that, okay, 1 second, guys. Okay, fine. So if you do that, this will also have some pressure, isn't it? That will also have some pressure. Now, obviously, what will happen is the total pressure will change, isn't it? Inside the container, the total pressure P total was due to this, this, and this. Now, the new P dash, I would say PT dash, that is the new one, will be equal to total pressure in the previous case. That is only due to N2, H2, and NH3. Okay, PP plus the partial pressure due to helium. Yes, right. Now tell me, guys, because of change in total pressure, right? Because of change in total pressure, do you think anything is going to happen? Will there be any change in the equilibrium constant? Say Kp, if I take, right? Kp will involve this, this, and this. Not this, definitely. This is not in the reaction, so that will not be involved in the Kp equation, right? So what I'm asking is, will there be any change to this value? Will there be any change?
Yes, sir, if delta n is not equal to 0.
Okay, okay. No, it's it's not that way, right? So how do we see it is, say in the Kp equation, right? You would have had, sorry, partial pressure of what is there? Head. Okay, NH3 would have been in the product side. I think squared divided by partial pressure of N2 into partial pressure of H2 cube. Correct. Right. So tell me, will there be any individual changes in these partial pressure of all these three components? Will there be any change in pressure because of adding this? Will there be any change in pressures of the partial pressures? I mean, will there be any change in partial pressures of all these three components? That's my question. Will there be any change?
No, sir.
No, right? So you will see that there'll be change in total pressure because of just the addition of this helium, but the individual partial pressures of these are not going to change. Definitely, right? Okay, so definitely, if that's the case, whenever you do it under constant volume conditions, there is no effect when you add a helium, when you add a inert gas to the reaction medium. Okay, please remember this. Right, I hope you understood the logic. When you do it under constant volume conditions, total pressure will definitely change because of the addition of the gas, right? But the individual partial pressures of the reactants and products are not going to change. That means the Kp value is going to be intact. There is no change in equilibrium, right? I hope everybody understood. Right. Okay. So now when I go for constant pressure conditions, right? So we'll see what is going to happen, right? I think I have to make some space this side. Okay, so now we'll take constant pressure conditions. So what do you mean by constant pressure conditions? It's like a balloon, isn't it? How do I put it? Say there is a vessel. Oops. Right. Say there is a vessel, right? But this vessel can now increase or decrease its volume. Is it not? Why is it able to increase or decrease the volume? Because when I add a new thing, right, when I add a new thing to this, since the pressure should not change, obviously when I add something, if it's a very insulated closed thing, pressure will increase, right? But I don't want that to happen, right? So what will happen? It's like it'll little expand or little elongate, something it will do so that the pressure is still constant even after adding the inert gas. That's what I'm trying to say, right? Okay, so you assume that you already had N2, H2, and NH3 here, and this is at constant pressure conditions. So obviously total pressure P total after adding and PT dash, in this case it's same after adding helium. That's the condition we took, isn't it? So now if you do that and you have to make the pressure constant, what will happen to the volume of the vessel? Tell me. Right, I want
Increase.
all the definitely it is going to increase, isn't it? So just to accommodate this gas, it will also have some volume, right? And the pressure should not change. So definitely the volume of the vessel will increase. It's like a balloon. When you add more gas, the volume expands, right? So the volume will increase, right? Now, what are you indirectly doing? You are increasing the volume, and this definitely is a reaction where delta N is not equal to zero. So whatever you saw for increase in volume, the same thing you will see here also. The reaction is going to move to a side which is going to have more stoichiometric coefficient. That's the answer. Okay, so indirectly, what I can tell, addition of inert gas at constant pressure is very similar to increase in volume. That's it. As simple as that. Okay, and when you're going to do the same thing at the constant volume conditions, there is no effect because only the total pressure will change, but the individual partial pressures of the components are not going to change. Okay, guys, everybody understood? Please give me a yes in the
So,
chat. Yeah,
can we also look at this way for
yeah.
constant pressure?
Mm.
Like the individual partial pressures, will it change or?
Individual partial pressure, will it change? Yes, it will change. Why it will change, I'll tell you. Now we have to make sure that the total pressure is same, isn't it? Now obviously when I'm going to add this, right, so you are going to accommodate that the individual partial pressures will change definitely. How do I put it? If you ask, you are adding one more gas also, so just to accommodate this gas the volume is increasing, isn't it? So the
Yes, sir, I
partial
got
pressure
that.
of all these components will decrease. Actually, that's what will happen, right? The Kp value will be actually depending on the powers and stuff, but eventually I can say that the partial pressure of this and this will decrease because there is increase in volume. That's all I can say. Yes, understood?
Yes, sir.
Okay, fine. Guys, everybody understood? Please give me a yes in the chat, or you can unmute yourself and put it. Yes, no, quick. Okay, one, two. How many are there? I think five are there. Okay. Others, quick, guys. Understood or not? What happened? Harish, Rahul, I don't know who answered the Sanjana or Sri Harini. Who was that? I think they now asked the question.
Harini, sir.
Okay, Harini. Fine. Okay. Right. Okay. Fine. I hope everybody should have understood. Right. Now, one more last way by which you can disturb the equilibrium, but not exactly. So the last one is catalyst. Right now catalysts, let's say without a catalyst there is an equilibrium. Now like when you introduce a catalyst, actually there is not going to be any change in equilibrium. There is no effect actually because of addition of your catalyst. There is not going to be any effect, but what will happen is the time required to reach equilibrium, right, the time required to reach equilibrium, that decreases because the reaction is going to become faster, isn't it? Right, so the time required to reach equilibrium becomes lesser, right, becomes a faster reaction, but there is no effect in equilibrium, constant value, nothing will change. That's it, right? Only the time taken for the reaction to reach equilibrium will change depending on what kind of catalyst you have. You can either have activators or poisons. Activators will increase the rate of the reaction, poisons will decrease the rate of the reaction, but I would say generally catalyst will only increase the rate of the reaction, right? So the time taken for the reaction to reach equilibrium, it will be decreased. That's it. Right, so yeah, this part of the chapter is over, people. Right, so we'll quickly do some problems. How much time is left? Okay, we have almost 45 minutes left. Right, I'll just give my problem set. 1 second, just me wait for a moment, guys. Okay. So guys, let us do like previous time. Is it okay? I'll just send you the questions in the WhatsApp and you'll be able to see it. Is it okay?
Yes, sir.
Okay. I hope everybody should be fine. Right? Because dictating the question, you writing it, then doing it, so much time. Right? I'll directly go to the group and I'll send you the questions there. Guys, the question number marked 7, which is there in the, I'll send you the question. The question number marked 7. Okay, hope you're able to see it. Right, so it says that the concentration of oxides of nitrogen are monitored in air pollution and water pollution reports. At 25 degrees Celsius, this reaction happens and the equilibrium constant is given. And there's another reaction, for that also equilibrium constant is given. Now they're asking for this reaction, third reaction, N2 plus 2O2 giving 2NO2. What will be the equilibrium constant? That's what they're asking. Okay, how do you approach this problem, people? It is just like thermochemistry, except that you are not going to deal with enthalpy values, but you're going to deal with equilibrium constant values. Right? Now, thermochemistry, it's pretty easy, isn't it? If you just reverse the reaction, you reverse the sign. When you multiply throughout the reaction, you just multiply the factor with the enthalpy. But here, it's not like that. Hope you know what are all the properties. Can you tell me what are the properties, people? There are 3 properties, right? Tell me what are those with respect to equilibrium constants. What are the 3 properties? When you reverse, when you add or subtract 2 reactions, when you multiply throughout a reaction by a factor, what will happen to the equilibrium constant? Nobody remembers.
So when we reverse the reaction, when we multiply the entire reaction with a particular integer, or if we add a reaction, add 2
Yeah, that's
reactions.
what. What will happen to the equilibrium constant in all these 3 cases? Okay, guys, I think yesterday only we saw. How can you not remember? Or you want me to show it to you? What happens? Okay, see. So where was I? Where is it? Okay. So what do you see here? Where is it? Oh, this is law of mass action. Yeah, got it. Right. So did you see? Right. First one is it is okay. This is okay. First 2 points are okay. Now see what happened. When you reverse the reaction, what will happen for the equilibrium constant? Look at this and tell me. What is happening? Third point. You look at the third point. What is happening?
It's the reciprocal of the initial equilibrium
Obviously,
constant.
right? So whenever you reverse a reaction, the equilibrium constant becomes its reciprocal. That's the first point you need to understand, right? Second, when you multiply throughout by a reaction, multiply by a factor throughout the reaction, see what is happening and tell me what is happening.
It's raised to its power,
Exactly.
to the
Right.
factor.
So whatever, correct. So whenever you multiply by a factor, the new equilibrium constant will be the old equilibrium constant raised to the factor whichever you multiplied. So you can see the new equilibrium constant is k dash, right? You have multiplied by, oops, yeah, So you have multiplied throughout by a factor of n, so it became k power n. Right. Now the next one, final one, I told you whenever, now look at this, whenever I add two reactions, the equilibrium constant has to be multiplied. You can see here, right? The new equilibrium constant K is equal to K1 into K2. And if you subtract the reaction, it will become K1 by K2, right? Okay. So these three are the things which you'll be using there. Now go to the problem and solve it. So maybe you take for the first reaction NO plus half O2 giving NO2. You don't take the numbers, guys. You don't have to calculate now. Just take it as K1, K2. Okay, just take it as K1 and K2 for the first reaction. Take it as K1 for the second reaction. Take it as K2, and tell me the answer in terms of K1 and K2 only.
Sir, it's K1 into K2, the whole power 2.
K1 into K2 the whole squared. Okay, fine. Any other answers, people? I'm not sure. I have to solve the problem. Right, any other answers, guys? Guys, please don't sit idle. Right, it'll be really boring for you as well as for me if you're just gonna sit idle. Please solve it and tell me the answer. Okay, nobody has any answers. Fine. Okay, we'll do this. Right. So the first reaction is NO plus half O2 gives NO2. Say this is K1. I'll keep it as K1. Right. So the next reaction is half N2 plus half O2 gives NO. And what is needed? Say this is K2. For this reaction, the equilibrium constant is K2. And what we need is this reaction, N2 plus 2O2 gives 2NO2. Say this is K. Okay. So I want to know K in terms of K1 and K2. Right. Now, how did you exactly do thermochemistry? Just like that you do. Now, in the required reaction, I require N2 in the reactant side. That is one N2, one full N2 in the reactant side. So first we'll see where is N2. N2 is here and N2 is in the reactant side. No issues. Right. But what I need is one N2, but here only I have half N2. So just multiply this whole reaction by 2. So this will, K2 will become K2 squared now. Right. Okay. Now, next thing is okay, O2 you don't see because O2 is there in both the reaction. We'll go for NO2. Right. Now I require NO2 in the product side. Yes, NO2 is in the product side, but I require two NO2, but there is only one NO2. So definitely this reaction also has to be multiplied by 2. So this will become K1 square. Sorry, K1 square. Then what you have to do? Definitely you are going to just add the reactions. As simple as that. You don't have to worry. It will definitely come up to be true. Right. So when you add the reaction, it will become multiplication. So K, yes, the answer is correct, Kana. So K will be K1 squared into K2 squared. That's the answer. Wonderful. Right? Okay, we'll go to the next question. I hope everybody understood. Easy question. You just made, but in here numbers are given, you have to calculate. That's the only difference. Right. Okay. Now, guys, I think in the same question, the same page, actually you can go for the numbers are not visible. Oh, numbers are visible. Okay, go to the 10th question in the same picture. Question number 10. For the following reaction, equilibrium N2O4 giving 2NO2, Kp is equal to Kc. They're asking what is the temperature. Hope everybody is able to see the question. 10th question. right? What is the formula, guys, between Kc, Kp? What is the formula? I told you, right? There is a formula relating Kp and Kc. Did you
So
guys listen
it's
to the
Kp.
okay.
Kp is
Kp?
equal to Kc into
Hmm.
RT power
Hmm.
delta N.
Absolutely. That's the formula, right? At least one has listened to the class. Wonderful. Thank you so much. So here, this is the formula, right? So I have Kp is equal to Kc RT. Only for RT there is power delta N. Right? So fine. Just solve it and tell me the answer. Quick. Tell me the temperature. So they are given Kp and Kc are same, so you can cancel it, isn't it? Right? So basically RT. What is the value of delta N? It's basically 2 on the product side, 1 on the reactant side. So it's RT power 1 only. Right? So RT is 1. Right? And R value, I told you should use it as 0.0821. Right? So the answer would be 1 divided by 0.0821. So 1 divided by 8 will be, I think,
Sir,
1. Yeah, I think option B is the answer, approximately.
no, sir, I
Yeah, tell
have
me, tell me.
this doubt.
Yeah.
Why is it 0.082? Like, why do you have to use that?
Oh, why is because I know I use Kp in the Kp, or you can look at this in Kc. I use number of moles and volume. Generally, I use volume in terms of liters, right? And pressure also Kp. I will be using it in terms of what is that ATM, right? So whenever you have liter ATM present, you have to use the R value as 8.314. And whenever any other thing than this, we have joules. Whenever you have basically joules will have all the SI units. You have to use for pressure, you have to use Newton per meter squared, and for volume, you have to use meter cube, right? So all these things, if it comes, then you have to use the this thing R value as 8.314, right? And if it is in terms of calories, I know we have to use 2, right? So in this case, since you're using liter atmosphere, that's why it is 0.0821. Okay.
Yes, sir, okay.
Yeah. So I think the correct answer would be 1 by 0.08 will become, I think, 12.5. Is it correct? Or what is it? Okay, 1 divided by 0.08 will be 2. 1 divided by 8 is how much?
Yes, sir, it should be 12.18 Kelvin.
Yeah, 12.18. Correct. Right. So that's the answer. So B is the answer to this question. 12.18. Okay. Right. Now we go to the next question. I hope everybody understood. But today's class is pretty silent. I don't know what happened to you guys. Okay. No issues. So guys, it's marked. Question number 12 is a question now. Right. So it says a sample of pure PCl5 was introduced into an evacuated vessel at 473 Kelvin. After equilibrium was attained, the concentration of PCl5 was found to be 0.05 mole per liter. Right. And they're giving you the Kc value also for the reaction. Now they're asking what is the concentration of PCl3 and Cl2 at equilibrium? Right. Now I told you what kind reactions. I told you how to approach these kind of problems, right? You have to do something called as equilibrium table very properly. If you do that, you're set. Done. Tell me what is the answer. I'll give you 2 minutes. But I think for this question, I think so. One thing is for sure, isn't it? Since I'm doing introducing pure PCl5, right? I can say for sure that at equilibrium, the concentration of PCl3 and Cl2 should be same, is it not? And that's what stoichiometry says, isn't it? 1 mole of PCl5 will give 1 mole of PCl3 and 1 mole of Cl2, right? So whatever is the whatever is the concentration of PCl3 will be the same as of that of Cl2. Any answers? Okay, let me solve this question, or I'll just, you want some more time? Okay, so I have okay. So this is the reaction, right? So I don't know at time t is equal to 0, what was there, isn't it? I don't know what exactly was here. I mean, how much did you introduce? I don't know, right? So I cannot do the equilibrium table properly, but I can directly go to equilibrium, and they have told me that the equilibrium concentration of PCl5 is 0.05, right? Okay, now I can say for sure that this concentration and this concentration are going to be same. That comes from the stoichiometry. I can just keep it as x and x. I don't know what are the concentrations, but the number of moles of this and this will be same, right? And the volume is going to be same because they're all in the same vessel. So this has x, this also will have x, right? Now I can directly go to my Kc equation. You can substitute the values there. Kc is given as 8 into 10 to the power minus 3, right? Now that will be equal to this concentration into this concentration, that is x into x will become x squared divided by what is there, concentration of PCl5, which is 0.05, right? 0.05, that's it. So you can find x, and that is the concentration of PCl3 and Cl2. That's it. Okay, so I think it should be this will become almost 4, so answer should be 0.02. 0.02 and 0.02 should be the answer. Okay, done. Easy question, isn't it? Just you have to substitute it in the Kc equation, and you have to know this. The stoichiometry you have to know, obviously. PCl3 and Cl2 concentration at equilibrium will be same no matter what. That is logic, pure logic. Right. Okay, we'll go to the next question. Okay, we'll take this question. So guys, the question number marked 5 is your question now. Given the reaction A plus B giving C plus D, that question. Okay, for this, you can easily draw the equilibrium table. If you draw the equilibrium table, the problem is done. That's it. Yes, any answers? This is not that much of a tough problem, guys. If you really try, you would have got the answer by this time. Don't make me treat you like small kids. I can ask you to open your videos and show me what you're doing, right? And I can even unmute yourself. You know that I'm the host. I can just unmute I can unmute your what is that, microphones, and I can hear it. Don't make me do all that, right? So anyways, so I will do this problem. If genuinely, if someone is trying and not able to do it, maybe I should help. Right. Okay, so again the reaction goes like this. I have A plus B gives C plus T, right? Now they're telling at time T is equal to 0. I'm going to draw directly the equilibrium table, right? Okay, at time T is equal to 0, they're telling 1 mole each of A and B are taken in a 5-liter flask at 300 Kelvin. And they are telling 0.7 moles of C are formed, and this is at equilibrium, right? So they're asking, what is the final concentration of all the 4 species, A, B, C, D? What is the final concentration at equilibrium? That's what they're asking, right? So what is the question telling is 1 mole each of this and A and B are taken, and this are 0, right? So when I go for equilibrium, right, so I don't know how much has reacted. So some X would have reacted, right? And obviously from the stoichiometry, you can see 1 mole of this requires 1 mole of this. So X moles would have required X moles. So this will be remaining. And you can see 1 mole gives 1 mole, 1 mole gives 1 mole. So they can, this X moles will give X moles then. So X and X, right? Now remember, these are the number of moles, right? What I need is the concentration, right? So when I go for the concentration values, now the volume is given to be 5 liters here, right? So how will I write it? It will be 1 minus X divided by 5, 1 minus X divided by 5, X by 5, and X by 5. These are the concentration values, equilibrium concentration values, right? Now, in the question they've given C, if 1 mole each of A and B are taken in a 5-liter flask at 300 Kelvin, zero point 0.7 moles of C are formed. They have given that, right? So what they're telling, they're telling this C at equilibrium, that the number of moles is 0.7. That's it. We directly found the X value. They have directly given us the X value, isn't it? So this will be 0.7. This will, if this is 0.7, this is also 0.7, right? And 1 minus X would be 1 minus 0.7 is 0.3, and this will be 0.3. Now you can easily get the concentration values: 0.3 by 5, 0.3 by 5, 0.7 by 5, and 0.7 by 5. That's it. That would have been the answer for this question. Yes, understood, guys? Yes, no?
Yes, sir.
Okay, fine. What is the time? 11:15. We'll do one more problem. Maybe I'll give you a good problem. One second. I'm just searching for a good problem. Okay, maybe I'm not finding my question. Maybe I'll give you my own question. Okay, fine. Okay, this is the question, guys. I'm writing it here. All right. Say I have this reaction. Okay. Right. Say initially, right? Initially, I have taken 1 mole each of N2 and H2. Okay, 1 mole each of N2 and H2, right? And at okay, the total pressure is maintained, and that is the overall pressure of the container is maintained at 2 atm. Okay, right? And after the equilibrium has reached, they found that the Kp value was 5 into 10 to the power minus 2. Okay, the Kp value was found to be oh wait. Not required. Actually, you find the Kp value. Okay, please go for it. I told you how to approach these problems, right? Whenever number of moles is given and Kp is asked, not Kc. I told you you have to use certain things. Let me see if anybody tries. So exactly similar problem I mentioned in my when I taught you how to do the problems. Exactly similar. I didn't. I just have changed the numbers a little bit. That also, but not much. Only certain things are changed.
Sir, the final answer is 2x
Hmm.
square into 1 minus x by 1 minus 3x the whole cube.
Oh, you're having x in the thing. Hmm. Okay, why x is there? Okay, did I miss any? Uh, okay, let me check. Fine. Cool. I'll write the reaction again. Okay, so at time t is equal to 0, they said that 1 mole of this, 1 mole of this, and 0 of this. Now at equilibrium, number of moles I'm talking about. So say some x would have reacted in N2, and I know here one mole of this requires 3 moles of this. So what will be remaining is 1 minus 3x, and 1 mole of this gives 2 moles of this. So here it will be 2x, which will be remaining. Done. Now, next, what I have to do, I have to do everything in terms of pressure, people. Oh, yeah, you need X there. You need the X value, isn't it? I should have given it. Or the better question would have been, I should have given you the Kp value, say some 5 into 10 to the power minus 2. And I should have asked you what are the individual partial pressure of N2, H2, and NH3. This would have been a better question. This is actually a good question. This is actually the question, right? Okay. So, anyways, I'll do the problem for you, right? So, assume that the Kp value is given to us because the information given is little not sufficient for you to find exactly the Kp. Fine. So, hope you understand now. Kp value is given to us, and all these three values you have to find at equilibrium. At equilibrium, what are the partial pressures of N2, H2, and NH3? That's what we need to find, right? Okay. So, this is what I have in the equilibrium table: 1 minus x, 1 minus 3x, and 2x. Now when I write the same thing in terms of mole fraction, right? So it will be calculating 1 plus 1 2 2, it will be 2 minus 2x. Yeah, 2 minus 2x. So 1 minus x divided by 2 minus 2x, and this would be 1 minus 3x divided by 2 minus 2x, and this would be 2x by 2 minus 2x would have been the mole fraction, right? And I know the individual partial pressures of this. Hope you remember the Dalton's formula. PA is equal to P total into the mole fraction of that particular component, right? So in total pressure I've given you two. I think how much I've given? 2 atm, right? So now total pressure would be 1 minus x divided by 2x, mean 2 minus 2x into 2. That will be the partial pressure of N2. Same way it will be 1 minus 3x divided by 2 minus 2x into 2. This will be the partial pressure of H2. And for this, it will be 2x by 2 minus 2x into 2 would have been the partial pressure of NH3. Right? Now it's pretty easy for us. They have given us the Kc equation or Kp equation. Kp value they have given. So Kp is some 5 into 10 to the power minus 2, and that is equal to all this, right? I have to substitute it properly. So it will be 4x divided by 2 minus 2x. I'm talking about NH3 here, partial pressure, the whole squared divided by 1 minus x by, okay, it's actually 2 minus 2x. I'll write it like that because you're multiplying by 2. So 2 minus 2x divided by, okay, 2 minus 2x is already there, but it's going to get cancelled. 1 only is there. Okay, no issues. We'll just keep it there. So it is power 1 into 2 minus 6x divided by 2 minus 2x, the whole cube, right? And that's it. Now you just have to solve it for x. You will have a cubic, no, you'll have a square equation only coming. You'll get a quadratic equation. Oh wait, this will be power 4 and power 2. Yeah, quadratic equation is what will you get, right? Solve the quadratic equation, find the x value, substitute the x values in the partial pressure. These terms, these partial pressure terms, this, and this. That's what they're asking for. And that would have been the answer to this question, right? So if this problem actually comes in exams, guys, right, you really have to be really fast in doing the quadratic equation calculations. You have to be really, really fast. Okay, right, fine. That's it for today, people, and we have completed. No, I think I have to do a little bit more problems. 1 or 2 problems I will do next class, right? And we'll go for ionic equilibrium, right? And please don't be this silent, right? I don't know what suddenly happened to you, right? You were all little energetic and answering. At least you will tell, at least you guess. That's what that was happening. But this class was a little off track. Okay, fine. Maybe because it is Sunday, right? And maybe something else. Whatever it is, from next class, I hope everything will be fine, right? Thank you so much, people. We'll meet again next class.
Thank you, sir.
Yeah. Oh, there's
Thank
something in
you,
the
sir.
chat. Thank you. Thank you.